All right. So this video will mark the beginning of the end of the new material for us. Okay. We're going to discuss HPLC. All right. And we might get into UHPLC, but they're pretty much they're very similar. We might get into other chromatography detectors and methods. But this will be the last major topic I think that we discuss for this course. Okay. So HPLC stands for High Performance Liquid Chromatography. Okay. And like all chromatographies, it involves a mobile phase and a stationary phase. In our case here, our mobile phase is going to be some liquid. All right. It's going to be some kind of liquid, be it, water, and acetonitrile. Or it could be water plus formic acid, right? Or it could be, any number of liquid mixtures, okay? And then we'll have our stationary phase, okay? Which is going to be a packed column of resin-coated polymer beads. Okay? Now, because liquids are not compressible, this will give us very high back pressures, all right? And as a result, we have specific instrumental things that we have to consider for this this type of material. All right, and we'll discuss those as well. All right. First, we should discuss the types of HPLC. Okay, you have reverse phase, and you have normal phase. Okay, those are our two key types. Okay, and they are opposites of one another, unsurprisingly, right? So in normal phase HPLC, we have a polar stationary phase and a non-polar mobile phase. MR. What's MR? Mobile phase. Okay? So this would be something like silica as the stationary phase, and then hexanes as the mobile phase, right? Supercritical supercritical CO2 is sometimes used in this kind of chromatographic setup, but that is given its own class of chromatography, okay, and that is supercritical fluid chromatography. All right, and that will be something we discuss after we're done with HPLC. All right. In reverse phase, you have a nonpolar stationary phase with a polar mobile phase. Okay. So here we would have, something like a carbon 18 bonded resin for the stationary phase, and then we would have water and acetonitrile as the mobile phase. All right. In addition to these two liquid chromatographic methods, Okay, we also have ion chromatography. All right. And ion chromatography you can be divided into either cation or anion based on what you're trying to analyze. Okay? In cationic chromatography, you have a negatively charged stationary phase. All right? And typically we control the amount of bonding or the elution control with the pH of the mobile phase. Okay? And that's true for anion as well. Okay? The difference with anion is that our stationary phase is positively charged. All right? Okay? Ion chromatography uses the same instruments as reverse and normal phase chromatographic systems. Okay? The only thing that's different between these three techniques is the mobile phase constituency, possibly the physical characteristics of the pump, because you need, if you're doing normal phase chromatography, you need a pump that can withstand organic solvents. Okay. Or if you're doing ion chromatography, you need a pump that can withstand the acids and bases that you are putting in, which is less of a concern for just normal reverse phase HPLC. Okay. Um, but the physical characteristics of the actual instrumentation, the components of it, um, other than changing by subtle detail, are essentially the same. Okay, so I want to go over all the parts of an HPLC first, and then we can go over um, these specific techniques. Okay, all right. So if I were to draw a block diagram of an HPLC, okay, I would have eluent reservoir. Actually, I shouldn't even call it that, and I should make this bigger. Okay, it would be mobile phase reservoir. Okay, and that is drawn through to a pump. Okay, all right, and this is a very simple one. All right, that goes through an injection valve where we can inject our sample through the injection loop. Okay, this whole thing outlets to typically a guard column, and then the analytical column. All right, and then that analytical column sometimes has things after it, but most of the time just goes straight to the detector, and we outlet that to waste. Okay, now there are various characteristics that we need to take into account for each of these components. Okay, starting here with the mobile phase reservoir. Okay, so our mobile phase reservoirs, one of two things has to happen. Okay, well, first we need to have our mobile phases degassed. Okay, we have to have our mobile phases degassed because the high pressure can force dissolved gases to form bubbles. Okay? And we see that there is a bubble in our system if we look at the pressure over time, and we see that it keeps oscillating between a low pressure and a high pressure. That indicates that there's bubbles trapped in the system. Okay? All right, that indicates there's bubbles trapped in the system because it gets low pressure when the bubbles are compressed, and it goes high pressure when the bubble is not compressed. Okay? And in order for the chromatographic separation to be efficient, we need to make sure that our pressures are staying constant. So this is a bad thing. Okay? The other thing is, all right, we have to make sure that the mobile phase is either under pressure or in some way is drawn into the pump without gas. Okay? We need to make sure that that mobile phase does not develop any air bubbles in the pump. All right? Because that will cause this same problem, right? The pressure will drop and then it will go up, and then it will drop and then it will go up, and then it will drop and then it will go up. Okay? All right. So, to degas our mobile phases, we have a few options. Okay, first, we can sonicate. We sonicate it under vacuum. Okay, we can do a cold vacuum filtration, where we actually take our mobile phase and we chill it down really far, and then we vacuum filter it into a new flask. That helps get all that gases out. Or ignore the disappearing C. We use a mechanical diaphragm degasser. Okay, these first two techniques are considered offline because we have to do them away from the instrument. The mechanical diaphragm or membrane degasser, though, that's an online technique. Okay, we put that between the reservoir and the pump. Okay, that way the reservoir eluent gets, or the reservoir mobile phase gets pushed into the degasser. The degasser removes any gases that are dissolved in it, and then we push it in. Okay. The fourth option, okay, is we do sparging with helium. Okay. We choose helium because helium is a very small molecule in terms of gas size. Okay. And it will help eliminate any other gases like oxygen and nitrogen and carbon dioxide that are dissolved in our mobile phase. Okay, and then we after any of these offline techniques, we have to then store our mobile phase under helium as well to minimize the chance of other gases being able to get in. Okay? So the other half of this is that we either have to be able to prime the pump physically, or we keep the mobile phase under pressure, okay, to assist us in pump priming. Okay, so this allows us to prime our pump. All right, which is putting in mobile phase into the pump to eliminate air from the mechanics. Okay, so we have to push all the air out. So what we actually do with these mobile phase reservoirs, instead of pumping them into the side, like you might think, what we actually do is we bring them around and we actually pull it into the pump, push it into the pump from the bottom, and then the pump usually outlets out the top. Okay? As opposed to out its side. That way, any air that's in the pump, okay, and we have a little valve here, any air that's in the pump can be forced out, and then the lines are free of any gas. Okay? I'm going to leave the block diagram up, so I'm going to erase all this by hand. There we go. Okay. So those are our two major considerations for our mobile phase and its reservoirs. Now, some instrument manufacturers will actually take a multi-layered approach, which is really good, and they will have degassing built right into their mobile phase reservoir controllers. I know Dionix, which is now Thermo, does this. They have online helium sparging built into the mobile phase reservoir platform, and then you keep your eluents under pressure, and they also recommend that you offline degas it before you even put them in, so that there is near zero gas contamination in your mobile phase. Okay, and then the pressure, the helium pressure, helps push your solvent, your mobile phase, into the pump. That way, priming it is very easy. You just turn the pump on full blast and put the outlet to waste. Okay? And that will allow it to suck in enough mobile phase that all the gas bubbles in the pump heads get eliminated. All right. Other manufacturers don't do this. They don't have the gas under. They don't have the mobile phase under pressure. It's not technically necessary. You can prime a pump by simply drawing enough material through it. Sometimes you assist it with a syringe, because once you get, especially if you have your mobile phase reservoir stored up physically above the pump in the instrumentation, which I will show you in a drawing later, that will create a siphon. And so your pump will continually draw. Once that first bit of priming has been established, your pump will continually draw mobile phase from the reservoirs, with them only being under atmospheric pressure. They don't need to be under external or extra helium pressure. So that varies by manufacturer. Some manufacturers have degassing units built right into the back of the pump. So before the mobile phase even reaches the pump, there's a degassing unit that it goes through. Some don't, and you have to buy an external mechanical degasser. It really is variable based on the instrumentation and the manufacturer of it. Okay? All right. So, pumps. Let's talk about the pump. So our standard pump is a reciprocating piston pump. Okay? And so we have a piston here that is attached to a mechanical cam. All right? And that cam is attached to a sapphire rod. Okay, and sapphire is chosen because sapphire is one of the most durable materials that we can make, and the rotating action of this cam, all right, will move the pump head back and forth. Okay, and this pump head is fitted into a very tight physical chamber, so that on the backstroke it draws material in, and on the forward stroke it pushes material out, and we regulate that using ball check valves. Okay, and the ball check valves are set up in a very specific configuration so that fluid can only go in one direction. So in each of these valves, what you have, okay, is a ball. All right, you have a ball. And when the ball is pressed up against the narrow end, it seals the valve. Okay? What that does is that only allows fluid to flow in from this direction, because if you try to push out this way, the ball is going to seat against the base and it's going to lock up. Right? So on the backstroke, this ball check valve opens, allowing fluid to fill the pump head. Okay? And then on the forward stroke, it's all pushed out this way because this ball check valve is seated during the forward stroke, and so it exits the pump there. Okay? Now, as you can imagine, this can cause some serious pulsing in our fluid flow, right? Because it's only every forward stroke that we're getting any pressure, right? And so most pumps will have a pulse dampener built into them. Okay, and that's just a chamber that takes the eluent and it allows it to be pressurized, and then it maintains it as a constant pressure source. So you can kind of think of it like a capacitor in an electronic circuit, right? It's building up pressure and then it's holding it there constantly, so that during the reverse stroke the pressure does not drop. All right. Okay. So pump requirements. Oh, I forgot one minor note. These balls and these ball check valves are typically ruby. Okay, uh, we use sapphire rods, ruby balls because of their mechanical durability. Okay, and if you look up those two minerals, they're both aluminum oxides, which is really interesting. Okay, so pumps have very specific requirements. The first is they must be able to handle pressures up to 6,000 psi. Okay, so these pumps need to be able to handle up to 6,000 psi. Typically, if you manage to get a pump up to 6,000 psi, the pump will be fine. Your lines will explode first, okay? Because your fittings or your actual physical line material will not be able to handle that pressure, and so it will fail mechanically well before you reach 6,000 psi. The only material I know of that can handle up to that high of a pressure is stainless steel. And we do have stainless steel fittings. We do have stainless steel um, tubing that we use in very high pressure systems like that. Okay, um, we need a pulse free output, right? Because we don't want our pressure changing. We don't want our pressure changing. So there's a few different designs for this. A lot of times, this single cam pump head is repeated at least 2 to 4 times in a single pump. Okay, so that when one pump head is on the reverse stroke, the other pump head is on the forward stroke. That way the pulse dampening is minimized. And then on top of that, they go into a pulse dampener. Okay? All right. They need to be able to handle flow rates. All right? Flow rates from 0.1 mils per minute to about 10 mils per minute. Now, certain very narrow bore pumps, okay, they cannot handle this high end of flow, and they can go much lower than 0.1 mils per minute. But most general HPLC pumps are in this region where they can handle 100 microliters a minute to 10 mils per minute reproducibly. Reproducibly is the key, okay? Because their flow reproducibility has to have a 0.5% RSD or lower. Okay, so we want this, when we program in a flow rate to the pump, we want it to be able to give it to us from start to finish with very little fluctuation. Okay, and then finally, it must be resistant to solvent corrosion. All right, so those are our 5 key characteristics of a pump. All right. There are also other kinds of pumps rather than a simple reciprocating pump. Okay, you can have syringe pumps. Okay, and these have a physical glass, usually glass syringe, sometimes plastic, okay, that is connected to your system. All right, and the plunger is controlled by a stepper motor. Okay, so there is a physical motor that depresses the plunger in the syringe, which gives you a steady input. Okay, syringe pumps are typically not used for very large flow rate systems because you still need a regular pump to deliver this, constant flow to get your chromatography going. Syringe pumps are typically used more for controlled sample introduction into a flowing stream. Okay. There are also other kinds of pumps like Milli Gap Pumps, which utilize a ring of chambers, okay, and a chamber fills, and then on the other side, the chamber is pushed clear. Okay, so it's kind of the reason it's called a milligat is because they handle very low flow rates, very reproducibly with very little noise, and they resemble a Gatling gun. Okay, in both physical appearance and in function. Okay. So those are just a few of the alternative pumps. Okay. From these pump heads, right, the first thing that happens is we get a pulse dampener. Okay. And then depending on your instrument design, you can either have a proportioning valve in front of the pump, or there could be some kind of mechanism to proportion your solvent after your actual physical pump head. It depends on your instrument manufacturer design. Most common, I think, is before the pump. All right, and we will talk about sampling valves, solvent proportioning valves, in the next video. Okay, and I'm going to draw a nice schematic for you as well. All right.